In our study of special relativity, so far we have seen that special relativity is based upon two postulates. The first postulate states that laws of physics are the same in all inertial frames. And the second postulate states that the speed of light is c, 3 times 10 raised to 8 meters per second. It's constant in all inertial frames. It doesn't matter whether the frame is moving with respect to the observer or at what speed or if it's at rest. So the speed of light does not change. Of course, one has to keep in mind that we are talking about speed of light in vacuum. If light was traveling in a material medium, it would have a smaller speed, like in glass or water. However, as long as you are considering vacuum, the speed of light is the same in all frames of reference. So those are the two underlying postulates. And then there are two consequences of these postulates that we have looked at. The first is the idea of simultaneity not being absolute. So events that appear to be simultaneous in one frame of reference may appear to be not non-simultaneous in other frames of reference. The second consequence we learned about was time dilation, basically meaning that if an object is moving with respect to an observer, then the flow of time appears to be slower to that observer. So for example, if you have a clock moving with respect to you, the clock would appear to be moving slowly, or the time would appear to be flowing at a slower rate. Now, one thing we observed in the context of time dilation, so we say that, let's see. So this here is the equation for time dilation. Delta t is the time measured by an observer who's in motion relative to the event taking place, and delta t naught is the time interval relative as seen by a person who's at rest relative to the event. And we call delta t naught, where is it? We call delta t naught the proper time. And that, yeah, delta t naught is called the proper time, and that is a bit of a misnomer. It can lead to confusion, but what I do want to make clear is that neither delta t nor delta t naught are more correct than the other. They're both correct. It's just the nature of reality that time in different frames of reference passes at different rates. So you can't say that one time is more correct than the other. Okay, so now we turn to a third consequence of special relativity, and that has to do with how space behaves, how spatial measurement is affected by frames of reference. So like time measurements, spatial measurements are also affected by the motion of a frame of reference. So spatial measurements are not absolute anymore, but are relative, meaning the length of an object could be 1 meter in one frame of reference, but 1.5 meter in another frame of reference. So again, we are going to use this unfortunate term of proper length, L naught, which is the length of an object measured by an observer at rest relative to it. So if the object and the observer are at rest, the length that's measured is called the proper length, L naught. So let's consider the following example. Let's say an observer on Earth is trying to measure the velocity of a moving particle. So let's say the particle starts at point A and is going towards point B. Now the observer is at rest with respect to the space being measured. The space being measured is the space between points A and B. So the observer is at rest with respect to that space. So we can say that the distance between A and B is L naught, the proper length. The time that elapses as the particle goes from A to B, however, is not the proper time. The time, we're going to use delta t for that and not delta t naught. The idea is the object that is being timed, the particle that's going from A to B, is moving with respect to the observer. So the time that the observer measures is not the proper time, but it's delta t. So using velocity as distance over time, we can say that v is L naught over delta t. Now let's consider an observer who's moving with the particle. So the observer is moving with the particle. So as far as the observer is concerned, the particle would appear to be at rest. So the distance between points A and B that this second observer will notice is not the proper length, but length L. That distance is L, since the space is in motion with respect to the observer. Again, the observer is attached to that particle which is moving from here to here. As the particle and that observer move from A to B, the space, the intervening space, appears to be moving backward. So because of that, we call that distance L and not L naught. The time which is measured, however, is delta T naught, since the observer is stationary with respect to the moving particle. So the velocity now can also be written as L over delta T naught, distance over time. The two velocities, we're talking about the same velocity in both cases, so they have to be equal to each other, which means L naught over delta t is equal to L over delta t naught. Now, from time dilation, we saw that delta t and delta t naught are related with this equation. Delta t is gamma delta t naught. So if I replace delta t in this equation by gamma delta t naught, the equation becomes L naught over gamma delta t naught equals L over delta t naught. So you can cancel out the delta t naughts on both sides, which leaves you with the equation L equals L naught over gamma, or L equals L naught times square root of 1 minus v square over c square. Since gamma, you'll recall, is 1 over square root of 1 minus v square over c square. Now, gamma, as we mentioned in the last video, is always going to be less than 1, and therefore L will always be less than, gamma will always be greater than 1. Square root of 1 minus v square over c square is less than 1. So gamma is always greater than 1, and therefore L is going to be less than L naught. So this is known as length contraction, meaning moving objects appear to be shorter than if they were at rest with respect to the observer. And this is the equation that represents length contraction or space contraction. Let's look at problem number 13. So problem 13 reads, how fast would a 6-meter long sports car have to be going past you in order for it to appear only 5.5 meters long? So again, it's important to be able to figure out which length is L and which length is L naught. Now, when you say that a car or an object is 6 meters long, the assumption is that that's the length that you measured when you were at rest with respect to that car. And then the length that you measure when the car is moving past you would then be L. So in this problem, L naught is 6 meters and L is 5.5 meters. And we have to figure out how far is the car going. So in order to do that, I'm going to square the length contraction equation, both sides. So L square equals L naught square times 1 minus square root of V square over C square. And I'm trying to solve for V. So I can divide both sides by L naught square, which gives me this equation. And then add V square over C square to both sides and subtract L square over L naught square. And then multiply both sides by C square and take the square root of both sides. So that gives you the equation V equals square root of 1 minus L square over L naught square times C. And we can leave our answers as the multiple of C. So all you have to do is calculate the square root of 1 minus 5.5 square over 6 square, and that comes to 0.40 C. So the car would have to be going at 40% the speed of light in order for it to appear being 5.5 meters long. And that's the end of 28.3, which brings us to 28.4, where we'll talk about addition of velocities, how being in different frames of reference affects velocities or measurements of velocities.